Okay, well, thanks everyone for joining today, and thanks, Chris, very much for inviting me and for organizing this great seminar series. What I want to talk about today is slow and fast earthquakes, and in particular, I'll talk about the Copiapó Ridge, which is a region in northern Chile where I want to talk about these slow and fast earthquakes. Maybe as a small advertisement heads up, for the second part of this talk, which will be at LFE, so I'll be presenting this as a poster at AGU, so you can stop by if you want to discuss this in even more detail then. And I think the first part, Ansuke will talk about at AGU. So you can hear all of this again at AGU if you'd like. So let's start off by discussing what I mean when I say slow to fast earthquakes. A fast earthquake is essentially what we would have called an earthquake until 30 years ago, or what we still typically refer to as an earthquake. So here we see a slip model for the Chihoku earthquake in 2011 in Japan. So you have some movement on an interface. You can describe it with, for example, here with the slip, and this movement happens on a scale of seconds to maybe minutes if you go to these very large earthquakes. That's a fast earthquake. It sends out seismic waves that we can record as shaking, and in this case, feelers shaking. However, what we figured out over the last 30 years is that there are also slow modes of deformation that are transient. And the first one that we found are slow slip events. So this is the continuous east-west displacement curve of this GNSS monument called Albertard in southern Vancouver Island. And we can see that it regularly has these slip periods. So it's not actually continuous, but has slip periods. And now the signature looks very similar to an earthquake, just that the slip periods last for weeks. So that the same slip happens here as in an earthquake, but over a duration of multiple weeks. The same moment release, but no seismic waves because this happens very slowly. And that's why it's called a slow slip event. So a valid question to ask about SSEs is why we care about SSEs, because as I said, they don't cause seismic shaking, so they will not be destructive. Now, I think for me, the main reason why I think we should care about SSEs is that they interact with fast slip. So here's just one example. This is from the Iquique event in 2014. It was a magnitude 8.1, 8.2 earthquake in northern Chile. And these are continuous GPS traces. And what you can see here is that in the 8 months leading up to the Iquique event, there's this pre-slip happening. So there's a very slow and large slow slip event happening that then accelerates into fast slip. There are many more examples of this, of either slow slip events triggering earthquakes, or like slow slip events then turning into earthquakes, or the other way around, earthquakes triggering slow slip events. So we really want to understand how this splitting of fast and slow moment release on an interface works. We need to understand slow slip events. Now, slow slip events are not the only slow earthquakes. There are other candidates, or there are other like smaller versions of that. And I want to present two of them because I'll talk about them later in my talk. On the left, you see a waveform of a low frequency earthquake, and it somewhat resembles an earthquake. We have a P arrival and an S arrival. But what's very clear is that these onsets are emergent. So an LFE is a short signal with an emergent onset. It is highly repetitive. That distinguishes it from an earthquake. Usually, so earthquakes, we have repeaters, but most earthquakes are somewhat unique. For an LFE, we expect to see the same waveforms hundreds of thousands of times, so the same source triggering repeatedly. And it's also very different from an earthquake in the recurrence because it's burst-like. So an LFE occurs, if you have an LFE, it's very likely that within seconds you'll have other LFEs, and this burst might last a few minutes. And then if you have one burst in a day, you'll have multiple bursts in the day. So there are multiple levels burst-like. Now, related to LFEs are tremors. So here we see tremors. These are different stations over roughly 100 kilometers. And what you can see is you don't really see any clear onsets like you'd see it for an earthquake. But the waveforms still look very similar across all of these different stations. So for 100 kilometers, we have coherent waveforms, and we can invert where these waveforms might be coming from by just looking at the move out. And turns out this is a tectonic source. Now, what are these signals that last a couple of minutes? It's presumed that there is superposition of LFEs. So essentially, if you have a very dense LFE burst and you stack all of these waveforms, you can't actually resolve the individual LFEs anymore. Or maybe you can sort this out, but it's not easy to resolve. But what you see is this tremor, this sort of energy release that's coherent and looks like coherent noise across different stations. And I said LFEs are burst-like on different scales, and that if you have an LFE burst at some time in the day, you'll likely later in the day have another one. Same for tremors. So if you have a tremor burst, you'll have multiple other tremor bursts around it in both space and time, typically. Now, interestingly, tremors and slow slip events and LFEs are related. And the way it works is that LFEs and tremors are often a seismic signature of slow slip. It's the same figure I showed before, but now let's talk about what these blue curves here are. These blue curves are the tremor levels, so the number of tremors counted per day. You can see that exactly when the slow slip happens, this is the time when we see tremors. So tremors are a way also to track slow slip, and this is not even just in time, but also in space. So if we look at spatial resolution, you can see how tremor migrates with the slip that's migrating during the slow slip event. Now, you might ask, why are all of them called slow earthquakes? And this essentially boils down to the idea that all of these events, slow slip events, tremors, and LFE, follow the same scaling. So this plot from Elin Perosa shows is seismic moment on the x-axis, duration of the event on the y-axis, and up here, all of these bubbles are slow slip events. When we go down, we find tremors, we find LFEs. So all of this follows a linear scaling, so constant moment rate. And this is in contrast to fast earthquakes, where you have this cubic scaling with time. So moment scales cubically with time because the area grows quadratically and the displacement linearly. So it's a different slip mode, but all of them seem to fall onto the same slip mode. Now, many questions about slow earthquakes are open, and I just want to mention two of them here. The first is, we don't actually know what the mechanisms of slow earthquakes are. And when I say we don't know, we clearly have lots of information on this, lots of research on this, but we don't comprehensively know. So there's still a lot to answer here. And one reason why this is the case is that we don't actually know where slow earthquakes occur. So we have found evidence of slow earthquakes in some region, but there's other regions where we don't know if we have slow earthquakes. And in particular, we don't really have evidence for the absence of slow earthquakes in certain regions. So I won't answer these questions today, but I'll at least try to give you insights on these questions. And specifically, I want to give insights by looking at the Copiapó Ridge in northern Chile. So let's go to the Copiapó Ridge. This is the tectonic setting around the Copiapó Ridge. So we're looking at northern Chile. You can see the inset here. There's still roughly 500 kilometers to the north until we reach Peru, but it's still very much in the north of Chile. And in this region, we have seamounts, a ridge of seamounts, the Copiapó Ridge, the subducting near Copiapó. If we look at the interseismic locking, we can see it has a low locking degree here. So this is the yellow color. Just as a remark, down here, there is no data in our locking map, so this is not actually completely unlocked. But it has lower locking than around. What also makes this region interesting is that it's a seismic gap. So between the Antofagasta earthquake in 1995, the Iapel earthquake in 2015, there's a gap of maybe 5 degrees where no large earthquake has been recorded over 100 years. And it is unclear whether this 1922 earthquake had a rupture area that we show here, which is probably more likely given recent analysis, or if it broke the whole section. But in any case, we know the Copiapó Ridge also often stops large earthquakes. So we have this mature seismic gap with a low locking and subducting seamounts. Now, what makes it particularly interesting to study slow earthquakes is that this is the only region in northern Chile where we know about slow slip events. So Emily Clark-Svigny resolved a deep slow slip event in 2014 in this area with a magnitude of 7.9 roughly. There's another one in 2020. It's harder to resolve it properly because shallow earthquakes happen at the same time to distort the geodetic data. And there's evidence that there were earlier recurrences of this event in 2010 already. So presumably we have something like 5 to 6 year return period of this deep slow slip event. And we don't know about any slow slip events around. So let's put this into this scaling relationship that I showed you earlier on. So if we put the 2014 deep slow slip event in, it falls here. So it falls pretty much onto the one-to-one scaling at a rather low moment rate, but still consistent with the scaling. And in this talk, I want to see how much I can fill this plot. So the first question I want to ask is, well, do we have evidence for further slow slip events? So this will be part one of my talk, looking at this part. And then the second part is to say, well, we know about slow slip events, but do we see at least the deep ones? But do we see these associated seismic events that relate to them, so LFEs and tremors? So this is my part two. How am I going to study this? I'm going to use a bunch of different temporary and permanent networks. So in this region, there were several deployments from ISTER, but also GFZ, Universidad de Chile, GEOMA. In total, almost 200 seismic stations distributed here throughout this region. And in addition, about 30 to 35 of them had geodetic sensors associated. So we have continuous GNSS waveforms, continuous GNSS recordings, and also seismic waveforms describing the region. And now, as probably quite some people know, I usually do machine learning. So this is the most machine learning slide you'll get during this talk. I use the machine learning tool. It's a FaceNet picker and then PyOcta to associate to build a machine learning catalog and did all the reprocessing. What we found were roughly 165,000 events in 3.5 years. The relative location uncertainties are well below 100 meters. In some regions, we go down to tens of meters. So it's just because the event density is so high that you have lots of events in close proximity to constrain the location. So the absolute uncertainty is much higher, but the relative location uncertainty is very low. And the magnitude of completeness is around 1.5. And when I say magnitude of completeness around 1.5, I speak about the interface region that we look at later on. Clearly, for these deep clusters down here, it's substantially higher than this value. Okay, so now we got everything we need, and let's start looking at part one, slow slip events. And the title slide gives it away. We found another slow slip event in Copiapó in 2023. This is joint work with my colleague Diego Molina at ISTER, who did all the analysis of the geodetic data. So the first thing that Diego did is he processed all the data, he detrended it, he removed the common mode, and these are 3 stations, geodetic stations near the Copiapó Ridge, east-west displacement. And this is about a year on the x-axis. You can see over a large part of the year, it's completely flat. And then in September last year, there is a transient that lasts for about a month, maybe 4 to 6 weeks, and then it goes flat again. This transient has a peak displacement of somewhere around 7 millimeters. It's not particularly much, but it's definitely above the noise. So Diego then did a slip inversion for this. And what turns out from the slip inversion is that this is a shallow slow slip event. So here's the slip inversion. It's roughly 5.5 centimeter peak slip, geodetic magnitude somewhere around 6.6, and the duration, as I said, somewhere around 6 weeks maybe. You see the secondary deep slip patch. We are not certain if this is real. So we think it's rather an artifact of the inversion, but we are not absolutely certain about this pad. Maybe a remark, this is an offshore event constrained by onshore stations. So what's actually happening near trench is very hard to constrain. So there might be more slip towards the trench and a higher moment rate or higher moment. We can't really say this for sure. Now, what we next did is we plotted the seismic data on top of the geodetic slip inversion. And here each dot is one earthquake, and the size is the magnitude, and the color is the time during the sequence. And I think it becomes very clear immediately that there are seismic migrations going on. We start here with these darker blue dots, migrates down dip, migrates a little bit to the north here, and then migrates far to the south. You see these events out here, you see all these orange events here, and then it stops down here at the red events. All of this happens exactly at the same time as we see the geodetic migration. We looked at the magnitude distribution. It looks very much like a swarm and not like foreshock aftershock. So let's zoom in on this most interesting part, this initial sequence shown here in the box B. So the first thing that happens are these tiny earthquakes. They happen on August 25, all of them below magnitude 1.5. So they're very small. This is somewhere around our completeness magnitude. A couple of days later, we have a very fast migration. So this takes about 8 hours to wander from here into this very active cluster. This cluster stays active for 5 to 6 days and then goes quiet. we see the quiescence, which I already suspiciously plot here. So what happens next is that we have a magnitude 5.3 earthquake, the largest earthquake we see in the sequence, and then all of this breaks away. So we have aftershocks afterwards. So this is the first of the green events, and then we have the SSE migrating actually, and the earthquakes migrating over the full distance. If we look at the locations, what we can see is that all of these events happen on the interface, so at least the vast majority of it. In addition, we see events above here, in what appears to be splay fractures. So there's most activity confined to the interface, and then in addition, we see these splay fractures that happen in the upper plate. So we have upper plate activity above. You might also wonder what this dashed line is I'm showing here. So I mentioned we're in the Copiapó Bridge, and the Copiapó Bridge has subducted seamounts. And this is the approximate location of a subducted seamount that we see on the gravity anomaly. Now, the gravity anomaly is not exact enough to tell you exactly where the seamount locates. It might be slightly further north or south or west or east. But it's very clear that what's happening here is happening on the flank of the subducted seamount. Now, let's zoom out again. X-axis is time for all of these plots, and here I show you just the latitude. And what I showed you before was this onset sequence here. You see it all happens pretty much at the same latitude. And then we have a reactivation, and we call it reactivation. So we have this 5.3 event after the quiescence, and then we see a migration to the north and to the south, pretty much at 3.5 kilometers per day. That's a typical migration speed for a slow slip event. What's interesting is if you look at the GNSS data at the same time, you see that there seem to be, especially in the blue curve, two different slopes that break around the time of the reactivation. It's from somewhere around 0.1 millimeter per day to 0.25 millimeters per day. Now, the exact time where this happens is hard to pinpoint from the GNSS data, but it seems to be compatible that this happens when the 5.3 event happens that we see after this quiescence. You can also see magnitude over time, and I think it's pretty clear just how the density of events goes up during this time. So how we have clearly an elevated level of seismicity during this time that doesn't look like a typical foreshock aftershock sequence. So what is happening here? Our interpretation is that what we see is how fluid acts on a segmented interface. So that all of this starts with these small earthquakes here, and then we have a rapid fluid migration into this very active cluster. And in this cluster, the fluids really lower the effective normal stress because we have a high fluid pressure that releases all the shear stress, so it triggers all the earthquakes. At some point, the shear stress is released. That's why this cluster goes silent, even though the fluid pressure is still high. And the reason why it stays so high is that there's a permeability seal down dip, which then breaks with a magnitude 5.3. And once this is broken, the fluid can migrate throughout the interface and actually do this propagation of fluids throughout the whole reach. Now, you might ask, why fluids? Why do we think there might be fluids involved? And there are several indicators. The first indicator is that fluids are very commonly, or a mechanism we commonly believe is active in slow slip events. But we also have more specific things. The first is this activity on the splay fractures. Activity on splay fractures is typically related to fluid drainage, and in our case, the activity on splay fractures moves with the seismicity underneath, and it happens especially active over this most active cluster, where presumably we'd have the highest fluid pressure. The second reason is we have this subducted seamount. So seamounts, when they subduct, lift up the upper plate and bring more sediments that are very rich in fluids into the interface. So around subducted seamounts, there's typically fluid-saturated sediments. So there's a high fluid availability in the region where we observe this initial sequence. Where we observe this initial sequence. In addition, there are some tomographic images, but only using onshore data. So again, not extremely detailed, that show a high VPVS ratio here. Again, a pointer for high fluid availability in the region. There's one last thing we can look at. So this is the cluster I showed you before. This used to be the blue cluster, but now I color it differently. And here's the time since the first event in this cluster along this transect, so going from here down here. And you can see that in this cluster, we have a migration southward. So the most active seismicity migrates southward, at a rate somewhere around 3.5 kilometers a day, probably slowing down a little bit during this time. In this migration, we see secondary bursts. So we see this burst, and this. And this is a very typical signature for fluid-induced systems. So in induced seismicity, it's very common that you see these secondary pressure pulses that manifest then in seismicity pulses that we can see. So this as well is compatible with fluids. Now, I guess some of you will ask this question later. There are other things that are difficult about fluids. So the main question is, how can fluids produce a down dip migration over 6 kilometer depth difference? This is a good question to ask, and this is a difficult question to ask. So there are two options. The first is that you have an up-dip fluid seal that's very solid. And the second option is that actually more fluid is released as the seismicity migrates, and the fluid release point migrates as well, which is compatible with the fact that we have sediments along this whole seamount, so that we might actually release more fluid further down dip instead of migrating all the fluid from up dip to down dip. Now, there's one more thing I want to point out here. I mentioned that the resolution is pretty good of this catalog, and what you can see is that in this cluster here, seismicity is not actually continuous. So even though this is the most active cluster, it again has subclusters of where the seismicity actually occurs inside this region. So it seems that this whole interface is pretty much segmented into areas that host earthquakes, and even these areas that host earthquakes, if you zoom in, you'll notice that only sub-areas have hosted. Now, you might ask, is the segmentation stable, and do these swarms repeat on these segmented interfaces? So what we did is we reprocessed the data from the permanent seismic stations using the same workflow we used for the temporary stations. So deep learning picking and then relocating using a 3D model that we inverted from the more high-resolution temporary data. And indeed, there are further swarms, or let's say swarm-type events that we see earlier on. We have different years here, and every color is a year where we found swarms. 2020 is not technically a swarm because there are main shocks happening down here, the magnitude around 7. But then afterwards, this migrates very far north, so it's not a typical aftershock sequence. It's actually probably a triggered slow slip event, but that's a story for a different talk. What's interesting is if you look at the locations, you see this very clear overlap of the events in the different years in the swarm. So this is the initiation region, blue what we had in 2023, and then we see that 2020, 2015, 2018, we have this very clear overlap up here. And similarly down here, all of these events have activity down here at a similar region. What does it suggest? It suggests that we have the same drivers causing this. So that there are slow slip events actually going on in these years as well. Now, we can look even further back at another cost of data quality. So this is 2006, using regional data from the Chilean seismic network. There's a swarm, and we can go back using teleseismic data, and there's swarms dating back as far as 1973. Now, for 2023, we have geodetic data. For 2020, we have geodetic data as well, showing slow slip. For 2006, there's one GNSS station that shows slow slip. So we know for 3 of them pretty clearly that there must be slow slip. But the characteristics of the swarm make it quite likely that there are further events going on that are slow slip. Interestingly, the seismic moment between these events varies massively. It varies over 3 orders of magnitude. In the event we looked at, we had a seismic to aseismic ratio of around 100, so only 1.5% of the geodetic moment is released seismically. We don't know what this ratio will be for the other events, but it still suggests that if the seismic moment varies by 3 orders of magnitude, there's also wide variability in the geodetic moment released in this slow slip events. So let's get back to this plot. So we had the 2014 deep slip event, and we can add the 2023 shallow slow slip event, which also fits nicely on the scaling relationship, slightly higher moment rate than the 2014 one. And now if we are being a little more speculative, given on the seismic swarms we observe, probably there are further shallow slow slip events that should fall somewhere in this region when it comes to the moment release. We can't exactly say where because we can't actually calibrate this without more geodesy, and to be honest, also without seafloor geodesy, that we probably need to resolve the smaller slow slip events. So this finishes part 1 of the talk. We now know about additional slow slip events. the open question is still, well, are any of these slow slip events, either deep or shallow, also accompanied by low frequency earthquakes or tremors, as we observe them in regions like Cascadia or Nankai? And to do this, to figure this out, I performed a systematic search for tremors and LFEs on all of this seismic data from the almost 200 stations we collected. I'll start by discussing tremors, because tremors are supposedly the easier phenomenon to find because they have longer waveforms, and that makes them easier to find. So how are tremors typically detected? I mentioned that when I showed you this figure, I said, look, the waveforms, though the shape is similar between different stations. And the way to measure shape is that we take envelopes. So the typical way for tremors is that you chunk waveforms into reasonably long segments, in this case, 5 minutes. And then I calculate the signal envelope at each station. And then I cross-correlate between the individual envelopes and locate them using a 3D grid search. So you use the code from Aaron Wack. So in case you've worked with this code, you might recognize the figure even. So you see here the envelopes, and you can see how there's energy coming in, how they align, and how we can then identify where this event might be coming from. You might notice that we have 2 clear spikes in these signal envelopes here. So this is clearly an earthquake and not an LFE, not a tremor, but it shows the principle. So we do this on all our data, and we get a big bunch of tremor candidates. From these candidates, I already removed everything that we know is an earthquake. So we have the earthquake catalog I showed before, and we just remove everything that is an earthquake because we don't care about earthquakes. Now, this is clear. It's clear that not all of these are tremors, because tremor envelope correlation often will lead to false positives. So what can we do to filter these automatically? Because there are also too many to inspect.
Yeah, this is Chris. Can I just interrupt for a second and ask you to say 1 or 2 more things about how you knew it was an earthquake? When you say you got rid of all the earthquakes, so if you got to identify PNS, then you said it's not tremor?
So we simply used the earthquake catalog we had before. So so the earthquake catalog uses a FaceNet picker to detect earthquakes and then phase association. So it relies on the fact that we see clear P and S arrivals, and then that we can associate them. So we remove the tremor if during the tremor time and in the region where we see the tremor, there is an earthquake in the catalog. So there's a signal that had clear P and S arrival we could associate. Yeah.
Gotcha. Thank you.
Okay, so how do we filter all of these candidates? The way that I did it is to say, well, we know that tremors occur in bursts, and this is an idea that came from other people. So if they are bursts, and we can say, let's only keep events that happen in bursts, and we use what Aaron Wack suggested and is using for Cascadia, we use clustering. So we do DB scan, we cluster all of the detections, and we say if a cluster has at least 5 members, we keep it, otherwise we exclude it. Now, we do not use the depth for this clustering because the depth is pretty unreliable in envelope correlation. We only use the epicenter and the time difference. And if we do this, we get rid of the vast majority of supposed detections. So it turns out the vast majority are isolated detections, which is not what you'd expect for a tremor. And these detections we can now analyze by hand, and some look promising. So let's start by looking at this cluster up here. So I went through all the clusters that we saw and looked at them in the waveform. Now, we looked at this cluster, and it becomes pretty clear immediately that what we see are not tremors. We have this very repetitive, very regular pattern, exactly once per minute. These are air gun shots. We also saw nice migrations that we see here, but Dietrich Lange sent us a GPS track of this active seismic cruise, and it matches exactly what we see from the GPS track. So this is not a tremor, but I show this because it's actually nice, because it's sort of a resolution test for what we're doing. We have an actual source and also a source we didn't actually know about beforehand. And we can see that we get a pretty good resolution in terms of latitude as we can trace where the air gun shots are happening. So our method generally works. This is not a tremor though. So we go through the rest of the clusters. We have 562 clusters. 44 of them were related to this active seismic cruise. The vast majority, 476, contain impulsive onsets from earthquakes or mining. Sometimes you need to look at a different frequency band. So this is 1 to 8 hertz, and there's a P wave, there's an S wave, there's a surface wave. It doesn't look particularly impulsive in this frequency band, but in a higher band we can see it. And it's very clear that this is an earthquake from a regional earthquake, which we can actually pinpoint by looking at the catalog. Why did we not remove it in the first place? Usually because the earthquake occurs outside the region that we use to remove our events from, outside our event catalog. In 32 cases, we have later coda or surface waves of regional earthquakes. So this is an earthquake offshore Peru. So it's about 1,000 kilometers away. And here we see this is a surface wave. Again, not a tremor. 4 clusters locate in mines. And these are 4 clusters locating in mines that at the same time are not mine blasts. This is usually heavy machinery in the mines. So Chile has very large open pit mines. They can have 2-3 kilometer diameter, and they essentially have whole factories in there. So they have massive rock crushers and other industrial equipment. That's what we see over large enough distances that we can do envelope correlation and detect it. It's not a tremor. And then one example is the teleseismic P wave from the Münchmeyer earthquake, which we see at so many stations that we coherently can correlate it. And it's surprisingly high in terms of its frequency content when we see it arriving in Chile. Then 3 of them are a mix of different things. So we use this clustering to say we only want to find things that don't occur in isolation, but if different things that occur in isolation happen at the same time, it will suddenly trigger our criteria. So 3 of the clusters do exactly this, mixing teleseismics, regional earthquake coda, and mining, which leaves us with exactly 2 potential tremor clusters. And I'll show you what we see for these 2 clusters. So this is the first cluster. It's a tremor candidate that happens on June 23. So this is before our slow slip event that happens in September. And these are waveforms sorted by the supposed distance to the epicenter. So this goes around over more than 200 kilometers. And you can see that we have a very similar shape at most of these stations. Some are too noisy to do that. It's very cigar-shaped, which is already slightly odd because this is pretty smooth for a tremor. At least that's what people who work a lot in tremors told me. The whole signal is about 20 minutes long. So what we can do now is say, well, let's not take 5-minute slices to locate it, take the full 20 minutes and do envelope correlation on this, because then we have more significance in the result. So I did the envelope correlation on the 20 minutes. And what we see is that this event locates very close to shore here. What you can also see is the most likely location is at the surface. For comparison, the interface is somewhere here, 35 kilometer depths in this region. So it's very clearly not happening on the plate interface, even though we have uncertainties. We can also look at the spectrograms of this. So this is exactly the waveforms I showed you before, but now in frequency domain. And we can see that nearby, the frequency goes up at least to 20 hertz, but we see some energy above it as well. This is a very high frequency content for a tremor. Typically, you wouldn't expect anything above 10 hertz. So this is a very high frequency for a tremor. And again, it makes it very unlikely that what we observe actually originates from the plate interface, because it would have been attenuated at this distance. So this candidate is likely not a tremor. It occurs almost in isolation. I say almost because the other cluster I mentioned happened 7 hours later. Very similar characteristics, just slightly shorter waveforms. The frequency content of this tremor, this supposed tremor, is unexpectedly high, and it locates at the surface and definitely far away from the interface at 35 kilometer depths. What could it be? Our best guess, it's an underwater landslide, but that's just our best guess, and there are many other processes that might cause this. So if you have suggestions, maybe come at the end. It would be interesting if you have other ideas what this sustained 20-minute signal might be. So summing this up, there's no evidence for tectonic tremor. Nothing that we found actually resembles a tectonic tremor. Okay, so let's go to LFEs as the last part. You might ask, why do I look for LFEs if I didn't even find tremors, given that LFEs, if they stack, cause tremors? The main reason to look for LFEs is that we use a very different method. So for tremor, we use the envelope, which is kind of an approximation of the moment rate and how it changes over time. So we don't actually use the signal shape in detail. For LFEs, we go the other way around. We use a deep learning LFE detector that I developed in the beginning of my postdoc, which looks exactly at the signal shape. So we hope that it captures a different characteristic, and maybe we can find LFEs, even though we couldn't resolve tremors. So how does this work? We essentially treat LFEs like earthquakes. We take continuous waveforms, we do phase picking using this deep learning detector, we give it to a phase association that then associates the LFE PNS phases, we give it to non-log log to get absolute locations, and we hopefully get an LFE catalog out of this process. And we find somewhere around 10,000 LFE candidates. You can see it's pretty scattered throughout the region, but that's fine. We know that the uncertainties of this LFE detector are much higher than the ones that we have for an earthquake detector, so also the locations will be worse. But if we look at this, some aspects become clear pretty quickly. The first is we have clusters that are statistical artifacts from station distribution. If you have enough stations, you'll just randomly combine peaks to cause an event. And we had a lot of stations in these regions because same crews I mentioned earlier deployed lots of onshore stations in these regions to detect their airgun shots or to measure their profiles they were shooting. So these are just artifacts. We again see mine blasting. This cluster down here, you can look at a satellite image. There's a mine located here. We see teleseismic P-wave arrivals. This is from the South Sandwich, from magnitude 5.1 in the South Sandwich Islands region. Each vertical line is a detection time, and this is a teleseismic P arrival coming in here. Interestingly, it seems to be only specific core phases because we only see P arrivals from 100, standing at roughly 100-degree distance, but some of our detections are P arrivals. And some things, if we relocate it, occur at the seafloor. So this red star is an LFE detection, or the location of an LFE detection. The background are earthquakes for reference, and it's clearly not at the interface that you'd expected. Now, this is very anecdotal, what I showed you, and I clearly can't do this for every single event. So instead, we went down the way of saying, let's do this systematically and use the repeating characteristic of an LFE source. And the way you typically do this is template matching. So we took all the candidates, we cut out small cells that are actually overlapping. We take all events in a cell as templates and use stations from around it, and then template matched against the whole time history. So what we get out is that we now have for each individual detection, we know when it reoccurs. So if it repeats, how often it repeats, at what time it repeats. And we can also now look at waveform stacks. So we can just stack up the waveforms from each detection and get a much better signal to noise ratio example of the waveform. And then I went ahead and classified these families by hand. So the first thing I did is I looked at what time of day is something active, and is it clearly an anthropogenic signature. So this is time of day local, this is event counts per hour. And you can see this family, for example, is exclusively active during the daytime. This is most likely not an LFE because this is most likely driven by some anthropogenic process. In contrast, other families have variations throughout the day, but this is not clearly anthropogenic. If I was in doubt about anything, I always choose the category that would fit an LFE, so in this case, non-anthropogenic. The second thing I did is I looked at how many arrivals and what arrivals do I see. So many examples look like this. This is what happens if you stack surface waves, typically very monochromatic. If we zoom in a little more, very smooth outline surface waves. Often you only see a single phase arrival. While I couldn't tell you which phase it is necessarily, well, for this example, I know it's P wave, but generally unclear, one phase arrival. And sometimes you see two phase arrivals. I picked them here, even though you might debate what's the best way to pick it. Now, I show you data from one station. In analysis, I actually have 10 stations available at once because it's all the stations where you matched it. I decide to pick two phase arrivals if I see, and at least one station if I see two clean arrivals. So it's not actually about seeing them at all stations, it's just at some stations having two arrivals. And then we can classify by the recurrence. So this is a recurrence time plot where we have time on the x-axis and inter-event time between subsequent events on the y-axis, log scaled. So what do we see? LFEs have these vertical stripes. This means we have typical burst-like recurrence. And burst-like on different time scales, that's why we get a stripe, because we get longer inter-event times and shorter inter-event times, and this produces this stripe. In contrast, what we also often see is what I call a bimodal recurrence. So you have these short inter-event times, so you have bursts, but they have a characteristic duration. And then certain inter-event times are rare, and then you have a longer repeat again, which is common. This is typically some form of an industrial process. It's definitely not what you'd expect to see for an LFE. And then last, we have other recurrences. This can be Poissonian as for an earthquake. This can be foreshock, aftershock. This can be various things. Definitely not burst-like, not what you'd expect for an LFE. So if I put all of this together, I can plot it like this. So dot here is, each dot is a family. It's blue if it does not fulfill the criterion, and it's yellow if it fulfills the criterion that I set and that I list on top. So we can see is many signals have an anthropogenic signature, many signals are surface waves. If we look at burst-like recurrence, there's only a few events that have it, mostly in this area, and two-phase arrivals, pretty rare. So what we'd expect for LFEs is two-phase arrivals, burst-like recurrence, and not to be anthropogenic. And no family actually matches all the criteria for an LFE. So what do we see? So first class of events where you see lots of is mining. We see lots of surface waves coming from mining. This is probably not blasting, but heavy machinery. You see the time of day is very biased. It starts at around 10 a.m. and then slowly goes down over the day. Obviously, there's work going on during the night as well, but not full-time during the night. Has this typical bimodal recurrence. The second thing is we see body waves from mining. So this is two-phase arrivals, PNS. Timing, you see these horizontal lines. This is 1 day, 2 days, 3 days. So they have a very clear blasting schedule. They always blast around 2 p.m. in the afternoon. Copper mining, open pit mines. We see teleseismic P arrivals, only one phase arrival, strongest on what I show here in blue, the vertical component. This particular family comes from the South Sandwich Islands, and if you wonder why this distribution of recurrence times, there's a magnitude 8 event happening here, and we're essentially using template matching at a teleseismic distance to map the aftershocks of a magnitude 8 event. And then we have this signal, which I already label ocean bottom signal, and I'll show you below. It has two-phase arrivals. It's somewhat burst-like, timing is somewhat okay. But what we did is we said, okay, let's locate everything where we have two-phase arrivals. So I went by hand and manually picked PNS arrivals on the waveform stacks and located them in the 3D velocity model. Turns out the ones that I called mining before that have two-phase arrivals locate in mines, and then we have the remaining families locate at the surface and slightly offshore, or at 14-kilometer depths and 7-kilometer offshore. However, 14-kilometer depths is still 20 kilometers above the interface, which is well outside our uncertainty range. So definitely not a tectonic source of these events, most likely, again, some process happening, some marine process that we're observing. So summing this up, there is also no evidence for LFEs. So why don't we find LFEs or tremors? There's a couple of reasons that are possible. And the first one is their moment rate might just be too low, bit lower detection sensitivity. And to make this more quantitative, we actually used the same workflow and applied them to reference regions. We applied them to Cascadia and Nankai, where we know that we have LFEs and tremors. So on top, these are tremor detections for Cascadia and Nankai. I color them by time because this nicely highlights the migration patterns that we see. And on the bottom, these are LFE detections. And then we went the same steps of doing template matching for the LFEs, and actually we classified them. Turns out they classify according to the criteria we set out, and also we can locate them, and they locate near the plate interface. So workflow works. So let's compare how these regions are different. Now, the first thing you can compare is we can compare the geometry and the station coverage. So in the background in color, I show you SLAP 2.0, just as an approximation of the SLAP structure. And the dashed lines show the typical depth range in which we observe tremors, and black dots are our tremors. So we can see in these depth ranges, we have stations above in Cascadia and Nankai, same in Chile. So this depth range is very well covered. So our network is on top of the stations, on top of the potential tremor region. So we'd expect that we have a good coverage, at least in that regard. And then we can look at the density of the network, and our network in Chile varies over time, but it's definitely more dense than what we have in Cascadia. And it's also more dense than in Nankai, even though just slightly more dense. Now, the other thing is that we need to look at noise conditions, and I spare you the histograms, but the summary is we have the same noises in Cascadia or lower, at least at low frequencies. For Nankai, if we look at frequencies below 2 Hertz, we have similar noise, and then as the noise gets higher, as the frequency gets higher, the noise in Chile is higher by approximately 2.4 times. That is because in Nankai there are borehole stations deployed, which will just be better at higher frequencies. So summing this up, we would expect very conservatively that we at least see tremors LFEs if they have a similar moment rate to Cascadia or slightly bigger than in Nankai. Now, the moment rate bands that we actually see for LFEs and tremors in Cascadia and Nankai are narrow, so it's actually possible that that's the case, and Chile just has small tremors. Second point is, well, in the time we looked at, which is late 2020 to early this year, there is no deep slow slip event happening. So if only deep slow slip events would be associated to LFEs and tremors, we might have missed them. So the recurrence time might just be too long. I think it's rather unlikely, and the main reason is that that's not how we observe tremors in other regions. So in other regions, this, for example, Cascadia, in colored are detections of slow slip that we know from geodetic data, and you see how regularly in between we have tremor detections. So tremors occur in between geodetically cataloged slow slip events, so it would be unlikely to have complete quiescence for a couple of years here in Chile. Which leads to the probably most interesting question, well, maybe they don't exist. There are many explanations that might be about temperature, it might be about fluid availability. One explanation I also find interesting is microstructure. So this is a very nice figure from Armbruster where he shows that only small sections of the interface actually cause tremors, and these sections are stable over multiple years. So maybe we don't know what these patches are made of, but maybe these patches are missing in Chile. And it also sort of fits what I said in the first part about this fractal segmentation of the interface that we see for the swarms. So it's fragment in the shallow section already fractally segmented. We don't know how it's in the deep section. And there are many, many more explanations possible here on why tremors might not exist. And then the last point is, well, maybe it's just something else. So we made a lot of assumptions going into this, and I tried to explain most of the assumptions we made. But clearly our assumptions might be wrong when it comes, for example, to repeat times, to the exact locations, and so on. At some point, we might debate what for us is a tremor in LFE, and I think we don't really have a checklist for that. So I think that's the open question I just want to point out here. So let's wrap it up. We have, in the first part of this talk, filled this area up here, showing that we had a slow slip event in 2023 and probably further shallow slow slip events that are repeating. And then at the bottom, we showed that there are no LFEs or tremors, at least none that we can map, so there might still be smaller or very infrequently recurring tremors. To conclude, northern Chile hosts ubiquitous fast earthquakes. I guess we didn't doubt that. We have deep slow slip events for which we do not know about any seismic signature. We have shallow slow slip events that have seismic swarms associated to them, but we have no or only very small tremors LFEs. Now, this is not an explanation on how tremors LFEs work, but I hope it provides a good constraint to model the mechanisms of how slow and fast earthquakes work and how they interact. Thanks everyone for your attention, and I'm looking forward to the discussion.
Thank you very much. Fabulous, fabulous talk. Please join me thanking Giannis for a great talk. Yeah, lots of interesting things. Really cool. And then I can recommend to you, invite you to use that raise hand feature at the bottom of your screen. That'll help us put us in some kind of order. And then really encourage people to join the discussion, point out your question. Yeah, and go from there. Let's see. Maybe it's me. The surface segmentation that you talked about near the end, I guess with Armbruster and stuff, does that have do you expect that to be different at Cascadia versus in Chile?
I mean, that's a very good question. So I guess the main question that boils down to is, are the differences we see differences in the lithology, maybe, or are these differences in stress field? So do we just map certain stress field characteristics that are stable over multiple years? Or do we see lithology? I think in both cases, it's possible that they just evolve differently in Cascadia and differently in Chile. So I wouldn't say I expect necessarily that they're different, but at the same time, I don't think we have reason to believe them to be identical. We know that they have variations along strike, along dip. So we don't really know what causes them. I don't think Armbrester has an explanation for why exactly these tremor sources cluster in certain regions. So I think the big question is, why does this happen? But I don't know if we actually have insights on that, what causes them. I think without knowing what it is, it's very hard to say if we should expect to have it in Chile.
So you've applied this. Yeah, I made myself a question by the time you got to slide about 62, I guess it was, and then in slide 65 you answered the taking your technique and applying it to reference regions. You reproduce the results that LFEs are really there. So it's not that. And did you also apply it in California to the LFE catalog?
No, we didn't apply it. So we applied the LFE picker in California when I first developed it, and it generally works in California. It's a little difficult in California with the station coverage we looked at because it's very biased towards the Parkfield array, which has a small aperture. And we're kind of trying to reproduce what Dave Shelley had done in his catalog.
Right.
But generally, we find the events in California, and we can see that we have the right event rates per day and the right variations. The reason we didn't do it in this study is that we focus more on subduction zones. So it's just much harder to compare to California and a shallow strike split fault compared to other subduction zones.
Yeah, beautiful. Joan Gomberg, if you're okay with that, why don't you just voice your question? And other people, please raise your hand, join the discussion.
No,